Welcome to the lecture series of network theory. In today's class, we will learn about the application of another theorem which we also sometimes use in simplifying electrical networks, and that is Millman's theorem. First, we will learn about what this theorem states, and then we will learn how to apply this theorem in case of DC circuits. So let's get started. The Millman's theorem states that in an electrical network having n number of DC voltage sources along with their internal resistances connected in parallel can be replaced by a single equivalent voltage source in series with an equivalent resistance. Now in this electrical DC network, as we can see, there are several branches which are connected in parallel with each other. Now in every branch, as we can see, there are voltage sources connected with a resistance in series, and there is a load resistor which is also connected in parallel with that DC network. Through that load resistor, suppose we want to find out the current value which is flowing. Now apart from this load resistor, the rest of the network can be represented by a single voltage source and a resistor connected in series. Now we will see that what will be the value of that voltage source. The voltage value of that voltage source will be algebraic sum of the product of voltage value and the conductance of that path divided by the summation of conductance of all the branches, and also the equivalent resistance which is connected in series with that equivalent voltage source. That value can be obtained by 1 by summation of conductances of all the branches. That means reciprocal of summation of all the conductance of all the branches. Now let's see that how we can obtain these values of equivalent voltage source and equivalent resistance in the equivalent circuit. Here I have redrawn the same circuit where all the branches are connected in parallel, and apart from this load resistor, in every branch there is a voltage source and there is a resistance which are connected in series. Now we will redraw the circuit by their equivalent current sources and their resistance values. So when every voltage source will be transformed into equivalent current source, then with that current source every resistance which was connected in series with that corresponding voltage source now in the transformed circuit will be connected in parallel with that corresponding current source. So as per that, we will have the same number of current sources connected in parallel and also same number of resistances which will be again connected in parallel with each other, and there will be a load resistor which was there in our original circuit. Now as we can see here, all the current sources are connected in parallel, so the net current value of the whole DC network can be found out by taking the algebraic sum of all the current values. Now here in this circuit, as all the current are flowing in the same direction, so here the current values will be simply added to get the net current value. Now if suppose any current source is supplying the current in opposite direction, then that current value will be taken as the negative current with respect to the other current values. So that current value will be subtracted from the other current values, and that's why we are taking, or we are saying here, the algebraic sum of all the current values. So this will be the formula to obtain the net current value of the whole DC network. Now next we will find out the equivalent resistance of that parallel path. Now here, since from R1 to Rn all the resistances are connected in parallel, so we can apply the formula to get the equivalent resistance of a parallel path. So here if the equivalent resistance is R, then it will be 1 by R will be equal to summation of all the reciprocal of all the resistance values. So it will be 1 by R will be equal to 1 by R1 plus 1 by R2 and so on till 1 by Rn. Now next, from this equivalent resistance we will find out the equivalent conductance of that DC network. Now since we know the conductance is nothing but the reciprocal of resistance, so here if R is the equivalent resistance of the whole DC network other than this load resistor, then the equivalent conductance will be simply 1 by R. That means it will be G1 plus G2 plus G3 and so on till Gn, where Gn is the reciprocal of the resistance of the first resistor or of the first this branch, and G2 can be obtained by taking the reciprocal of that resistance value. So this way we can find out the equivalent conductance of that DC network. So the final equivalent circuit can be represented by a single current source having the value of this and also the equivalent conductance. And here the current source and the conductance will be connected in parallel. Basically this conductance is nothing but the resistive path, and only here the conductance value of that resistor or resistive path has been shown here. So the current source and that resistor will be connected in parallel, and with that the load resistor again will be connected back to that equivalent circuit. Now if we want to represent that circuit by a single voltage source, so we have to see that how we can find out the voltage value of that voltage source. Now we know that from Ohm's law that voltage will be multiplication of current and resistance value. So current we have already obtained in the previous step, and this is the value, algebraic sum of all the current values, divided by, if IR can be rearranged this way, I divided by 1 by R, and 1 by R we have already obtained by applying the concept of parallel paths in this step. So here the value of voltage of the equivalent voltage source can be found out by this formula. Now again, in place of every current value, if we can represent the current value by its equivalent voltage value, we can do this way. Since current will be voltage divided by the resistance path of that particular branch, so in place of I1 we can write V1 divided by R1. So it will be plus minus V1 divided by R1 for the first branch. Then for I2 it will be plus minus V2 by R2 and so on, divided by the same denominator that we had in the previous step. So this is the formula of V that we can obtain from this DC network. Now next is to represent the value of that equivalent voltage source in terms of their conductance. So V1 to Vn, they will remain as they were in the previous step, and in place of 1 by R1 or in place of resistance value, we will be replacing them by their corresponding conductance value. So for the first part, the conductance, as I said, can be found out by 1 by R1. So in this place, in place of 1 by R1, we will simply writing G1, and this way in place of 1 by R2, here we will be writing G2 and so on. So in place of 1 by Rn, it will be simply Gn, divided by 1 by R1 will be G1. So in the denominator it will be simply summation of all the conductance values of all the paths. So the final value of the equivalent voltage source, it will be the algebraic sum of the product of voltage value and corresponding conductance divided by the summation of all the conductances. Now we will see that in the final circuit, if we represent that by an equivalent voltage source and by a equivalent resistance which will be connected in series, then how we can find out the resistance value. Now resistance, again it will be reciprocal of the conductance, and conductance we have already obtained. So by taking the reciprocal of that conductance, we can easily find out the equivalent resistance value, and that will be 1 by summation of all the conductance values. So this will be our final equivalent voltage value, and this will be our final equivalent resistance value. Now next we will apply the concept of Millman's theorem their equivalent voltage value and equivalent resistance value, and we will solve a few numericals so it will be more clear. Now in this DC network, as we can see, there are few parallel branches, and in every branch there is a voltage source and a resistor which are connected in series, and there is a load resistor having value 1 ohm. We have to find out how much current is flowing through that load resistor. Now if we apply the concept of Millman's theorem, we can easily obtain the current value. Let's assume the current which is flowing through this load resistor, that is I. Now as per Millman's theorem, we know the voltage value of that equivalent voltage source. It will be algebraic sum of the product of every voltage value and its corresponding conductance. So it will be plus minus V1 G1 plus minus V2 G2 plus minus V3 G3 divided by G1 plus G2 plus G3, as we have three parallel branches in this DC network. Now the voltage value of the first voltage source, as we can see the polarity, the positive polarity is connected with the resistance, so it will be taken as the positive value. So it will be 4, and the resistance value of this path is 2 ohm, so the conductance value of this path will be 1 by 2. Similarly, for all other voltage sources, their polarity as same as the first one, so here the voltage value of other voltage sources also will be taken as positive. So it will be simply the voltage value, which is 2, multiplied by the conductance value, which will be 1 by 4, as the resistance value is 4 ohm, plus here it is 8 volts, so 8 multiplied by, it will be 1 by 2, divided by their conductance value, again that will be 1 by 2 plus 1 by 4 plus again 1 by 2, and simply it will be 2 plus 0.5 plus 4, and in the denominator we will have 0.5 plus 0.25 plus 0.5. If we further simplify this, then finally we will get the voltage value of that equivalent voltage source as 5.2 volt. Now in the next step we have to find out the equivalent resistance value. So it will be, as we have seen in the previous slide, that it will be simply reciprocal of the summation of all the conductances. So it will be 1 by G1 plus G2 plus G3, and that will be simply 1 by, here G1 plus G2 plus G3, as we have already seen that it is 1.25, so it will be 1.25, and finally it will come as 0.8 ohm. So in the final circuit we will have a resistor, equivalent resistor, and a voltage source which will be connected in series, and with that we will connect back the load resistor. So that load resistor has value 1 ohm, and this equivalent resistance has value 0.8 ohm, and this equivalent voltage source has value 5.2 volt. So the current which we initially assumed as I, that I will be nothing but the voltage value, which is 5.2, divided by the summation of all these two resistance values as they are connected in series. So it will be 1 plus 0.8. So it will be 5.2 divided by 1.8, and finally that value will come as 2.89 ampere. Now let's simplify another DC network by applying Millman's theorem. In this DC network, as we can see here, we have current source also along with voltage sources, and also the polarity of all the voltage sources are not same. So here what we will do in the first step, first we will convert this current source, and with this current source there is a resistor which is connected in parallel, so easily we can transform this current source to its equivalent voltage source. So the voltage value, equivalent voltage value of that current source will be simply the current value multiplied by the resistance value. So here it will be 2 multiplied by 1, so it will be 2 volt, and the resistance will be connected in series with that voltage source. So finally we will have 4 parallel branches, and with that parallel circuit we will have a load resistor through which we want to find out the current value first, and then based on that we want to find out the power loss finally across that 5 ohm resistor. So here, apart from this load resistor, we have four parallel branches, and in every branch there is a voltage source and there is a resistor which are connected in series with each other. Now, as per the Millman's theorem, the voltage value of that equivalent voltage source, it will be algebraic sum of the product of voltage value and its corresponding conductance. Now, the voltage value of the first branch is 4, and the conductance value will be 1 by 2, and since the positive terminal is connected with the load resistor, and this is the arrangement, so it will be taken as the positive value. The current is flowing in this direction, and since the current is flowing in this direction for the current source, so the polarity of the voltage source will be like this, so it will be again taken as positive. So the voltage value as we have obtained as 2 volts. So for that part, for that branch, it will be 2 multiplied by the conductance value, which is 1 by 1. So that means it is 1. And for this branch, here the polarity is opposite. So here the voltage value will be taken as negative with respect to the other. So it will be minus then the voltage value and multiplied by the conductance value, which will be 1 by 4. And then again for this branch it is the same polarity, so it will be taken as positive. So 8 multiplied by the conductance 1 by 2 and divided by the summation of all the conductances. So it will be half plus 1 plus 1 by 4 and again plus half. If we simplify further, then it will be 2 plus 2 minus 0.5 then plus 4, and in the denominator we will have 0.5 plus 0.5 1 plus 1 2 and then 0.25, so it will be 2.25. And if we simplify further, then it will come as 7.5 divided by 2.25, so it will be 3.333 volt. And next we have to find out the resistance of that equivalent resistor, and that will be reciprocal of summation of all the conductances. So it will be 1 divided by half plus 1 by 4 plus half, so it will come as 1 by 2.25, so it will be 0.444 ohm. That means in the final circuit we will have a voltage source and a resistor which will be connected in series, and the value of this equivalent voltage source will be 3.333 volt, and the value of this equivalent resistor will be 0.444 ohm, and with that branch the load resistor will be connected back, and the value of that load resistor was 5 ohm. So the current which will be flowing through that load resistor, that will be V divided by, directly we can write the value which is 3.333 volt divided by the summation of the resistance values, which is 5 plus 0.444. That means it will be finally 0.612 ampere. And now if we find out the power loss across that load resistor, then it will be simply I square R. So it will be 0.1612 square multiplied by the resistance value. So it will be 1.873 watt. So this is the way how we can apply the Millman's theorem to simplify a DC network. So with this, I end today's class, and in the next class I will be discussing about some other network theorem. Thank you.